Are white dwarf stars a perfect solution for Dyson spheres? How will Vera Rubin's data releases work? Where do Magnetars come from? And in Q&A Plus, does physics work the same way across the universe? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I'll answer them here. All right, let's get into the questions. Our visions. Could a Dyson sphere be located around a white dwarf, the smallest possible size, less material? Yeah, so a white dwarf, right, which is the leftover remnant from a star like our sun that dies. You've got the core of the star, still going to be tens of thousands of Kelvin. And they have a habitable zone, which is really cool. So it's about 4 times the distance from the Earth to the moon. So if you're within 1 million kilometers of the surface of a white dwarf, then you are within the habitable zone of that white dwarf. And then it is going to take billions of years for it to cool down. And that is a much more reasonable space to work with, right? You've got all of the leftover material in your entire star system. And we know that there are white dwarfs with planets, and so you're able to harvest all of that material. You nestle it up very close to the white dwarf, and you're within the habitable zone, and you're good to go for billions and billions of years. And in fact, there's this weird thing that white dwarfs do, which is that they stop cooling down at a certain point, and why they do this is sort of still not entirely known. I did an interview with somebody about this, but they seem to pause their cooldown rate for potentially billions of years. Something about the internal structure of it reorganizing itself, and that sort of buys you more time and keeps the heat going at the same level. And so, yeah, you could be some advanced civilization, your star has died, you have reformed an advanced civilization in orbit around the white dwarf at about 4 times the distance from the Earth to the moon, and you are surviving. And in fact, now you're building spaceships and you're harvesting more of the material around you, and you're continuing your existence for as long as our sun will be around. You could live around a white dwarf longer. And you don't have to worry about flares. You don't have to worry about people even spotting your civilization, because white dwarfs are relatively cool, relatively difficult to see compared to bright stars. Gonna be 2MS. Will LSST have regular data releases, or will we be in an attic-like state waiting for science data like the bulk of Gaia data isn't out yet? So the good news with LSST is that the data is going to be live. So there is a brief delay as the telescope is pulling down its live data, because it has to go from Chile to the US, where the Department of Energy removes surveillance satellites from the images. And then this information is in a live feed. And so as close to real time as humanly possible. And so what's going to happen then is, because Rubin is looking for events that are very short nature, right? You're looking for supernova, you're looking for asteroids moving, you're looking for Planet 9, you're looking for comets, you're looking for weird transient events. And a lot of the times, the faster you notice the supernova, the quicker you can turn telescopes on it and do follow-on observations. And so there won't be these big, long data releases. I mean, there will, but it'll be different, because the way Rubin works, and we got sort of a nice glimpse of this early on this summer, is that it's going to come back and image each spot in the sky dozens of times throughout the course of its 10 years of operation. And you know, normally with a telescope, you will say, do observations of a specific spot in the sky. You'll image the spot in the sky, and you'll do an exposure, and then you'll do another exposure, and then you'll do another exposure. And each time you do another exposure, your data gets better and better. You get more data, less noise. The image gets clear. The galaxies pop out, and you have, you know, however long you're doing your exposure to kind of make the observations that you want to do. With Rubin, it comes back every few days and takes another image, and then astronomers will be able to stack up those images to be able to look for things that have changed in those images, in addition to just really deep, high quality images taken, you know, over the course of 10 years. Like, you can get really beautiful, high quality images over time, building up one exposure at a time. But there will be ways to just dip your mind into the river of information that is flowing out of Vera Rubin and just like, oh, supernova, oh, asteroid, and watch these events. So they're building in filters that will identify the kinds of events that astronomers are looking for. They're building a pipeline. And then all of those data will be dumped into these gigantic hard drives, and astronomers will be able to go through those hard drives, or be able to run database queries on all of those data and look for the kinds of things they're looking for. So they can say, well, this region of the sky, show me all the supernova that went off from this time to that time. And they'll be able to pull up all of these queries. So you're going to kind of get the best of all the worlds, right? You're going to get something that's going to feel like real time, like you're watching a stock ticker, like you're watching a live event. You're going to be able to go through all of the data as quickly as it is made available. Just boom, because they're sort of doing all of the processing and rendering and pipeline immediately. And then there's going to be data releases as they're doing these big long exposures and releasing interesting information about the structure of dark matter, weak gravitational lensing, baryon acoustic oscillations, surveys of galaxies, things like that. There's going to be a ton of data releases on top of that. So yeah, it's going to be the best of all worlds. And I don't know when it starts. It's time to shout out our new patrons at the $5 level and above. Stephen, Don Whiskerando, Stephen Nichols, Rex, WeJoy, Kenny Hitt, Chris Thomas, Joseph Cain, Johannes Ekman, and Brad Mobley. Join our community at patreon.com/universe today. Karen Deepgill. How does the mass of the Milky Way galaxy's supermassive black hole compare to the mass of other galaxies in the universe or to nearby galaxies? So the mass of the supermassive black hole compared to the mass of the rest of the Milky Way is about 0.1%. So less than 1% of the mass of the Milky Way is the supermassive black hole at the heart. It has like 4.1 million times the mass of the sun. And the Milky Way has a lot of mass in it. It's thought to be 100 billion stars. I forget the exact mass, but it's like 1.5 trillion solar masses, something like that. And so, people always think that, oh, the supermassive black hole is like a big chunk of the mass of the Milky Way, but it really isn't. And that is fairly normal for galaxies in our epoch. So the galaxies we see around us, they have supermassive black holes that are kind of roughly that same ratio of black hole to galaxy. And those numbers can go up and those numbers can go lower. But a trend that is seen is as you get earlier and earlier into the universe, the ratio of the black hole goes up. And so you'll see black holes that are 2% the mass of the galaxy. And early on in the universe, the kinds of galaxies that you're seeing, say with James Webb, where they're just a few 100 million years after the Big Bang, the galaxies, like maybe 10% of the galaxy is the supermassive black hole. And one of the big outstanding questions that astronomers have is, what comes first, the supermassive black hole in the galaxy or the galaxy around it? And the traditional model, the lambda cold dark matter model of the universe, really kind of relies on this bottom-up formation of galaxies, that you have these smaller proto-galaxies finding each other, merging together, their black holes find one another, merge into a more massive black hole, and the thing gets bigger and bigger and bigger over time, and that the mass of the black hole remains in pace with the mass of the galaxy and all the material that's accreting around it. But if the galaxies have supermassive black holes that are much, much heavier than anticipated, then this could be more evidence that you're getting these direct collapse black holes, that instead of you having to go through this, you start with a little black hole, like a stellar mass black hole, and then two stellar mass black holes merge, and then more black holes merge, and eventually, and the black holes are feeding, and you work your way up to these bigger massive black holes. Well, maybe you have the direct collapse method. So you just have giant clouds of gas and dust that collapse directly into black holes with no intervening stage. And so that would give you an overly massive black hole compared to the galaxy around it. But this is all the fresh stuff, right? Like these are the weird mysteries that astronomers are currently working their way through. Hangman 747 Tin Man. I was watching your Magnetar interview. Could we look at the neutron to neutron star merger witnessed by LIGO and see if it became a magnetar? Well, that's the question. So in that interview, Dr. Genevieve Schroeder was saying that what they were looking for was that there should be some kind of radio signal coming from whatever is left behind after the two neutron stars merged. And a certain kind of radio signature would tell you that there could be a magnetar as the remnant. They didn't see a remnant. They didn't see that radio signal. Now, it could just be that it turned into a heavier neutron star. It could just be that it turned into a black hole. Could be that it just vaporized entirely and there is no remnant behind. But they got a null result on is it giving off this signal that would tell us that it is probably a magnetar. But, I think what you're asking is like, would you see the presence of a magnetar in the collision after the two neutron stars merged? And the problem is that you need to have mass that is moving for it to be able to give off gravitational waves. So while the neutron stars are spiraling around each other, getting closer and closer and closer, then you've got a ton of mass that is whipping around and you've got these gravitational waves that are emanating outward. Once they merge, then they turn into a black hole or a magnetar, or they vaporize. And now there is no longer moving mass. And so you can no longer detect the gravitational waves coming from it. If you see like the animations of these things, you see the neutron stars with the black holes going around each other, and you're seeing these gravitational waves that are going out, and then they merge into a thing, and then the gravitational waves are gone. Because now it is no longer this thing that's wobbling, it's no longer something with many times the mass of the sun wobbling around hundreds of times a second. It is just sitting there out in space. So unfortunately, LIGO can't help you find the remnant. Now I say that, but astronomers are very clever. And so I'm sure they're like, no, we think we've got a way. One idea is like you could potentially find lopsided supernova, where when the supernova goes off, even though it's just one star, it maybe doesn't explode as a perfect sphere. It blows off one side of the supernova first, and then that causes the rest of the star to jet off in the opposite direction. Now you've got gravitational waves. Maybe you could detect this. So maybe if two neutron stars merge together, then it's lopsided in some way, and it's kind of like wobbling around in this lopsided way. And then maybe you would get some gravitational waves coming from it. But if it does form this sort of perfect sphere afterwards, then you wouldn't be able to detect it in gravitational waves. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call that Q&A Plus. And this week's bonus question: does physics work the same way across the universe? I'll put a link in the show notes. All right, those are all the questions that we had this episode. Thank you everyone who asked your questions in the YouTube comments, everybody who joined me for the live show. Now, we do the next live show on Monday, February 16th at 8 a.m. Pacific, which is evening for Europe. So you're welcome, Europe. But I'll put a event here on the channel so you can check out when that's going to happen. I'm going to talk about some upcoming science fiction that I'm pretty excited about. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barry Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bieluk, Dark Finga, David Giltonen, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Matter, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Robach, Rankaidu, Richard Williams, Sean Sargent, Stephen Fowler-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So there are a few science fiction TV shows and movies that are coming out very soon, which you should sort of, you're going to want to reorganize your schedule so that you can take advantage of all of these. So the first one, and this is the thing that I'm probably most excited for the upcoming year, is Project Hail Mary, which is going to be premiering in sort of mid to late March. And of course, this is a adaptation of Andy Weir's book, Project Hail Mary, which is just a page turner. Like if you haven't already read the book, I know you will love it. If you enjoyed The Martian, you enjoyed The Martian book, you enjoyed the Martian movie, you're going to love both the book, and I'm sure the movie is going to be good. It's essentially the same team that did The Martian, as well as the Into the Spider-Verse and a bunch of other stuff, and then they're doing this. It's got Ryan Gosling as the main character, and there was a new trailer that just came out, and they've given away everything. So, it's hard to sort of give you spoiler alerts on this. Like if you watch the new trailer, you're going to see sort of the entire gist of the show and what started out being a surprise in the book. It's weird they got down this direction, but that's fine. They're in charge. I can't wait to see how this is put together. And then there's a couple of TV shows that are going to be giving us new seasons in March, which you might want to catch up. The first one, I think the most important one, is going to be For All Mankind. So in March, we're going to see the new season of For All Mankind. And so if you are excited about For All Mankind, or if you're like wondering, sitting on the fence, this might be a good time to get your Apple TV subscription, catch up on Silo and Pluribus, and then catch up on all the episodes of For All Mankind. It is one of my top 10 science fiction TV shows ever list. So you might want to catch up on For All Mankind. And then we have the new season in mid-March. Then we've got a new season of Invincible, which is, again, one of my favorite TV shows. I really love Invincible. So that's coming out. And then there's going to be a second season of One Piece, the live action, which is on Netflix. So if you want to catch up on any of those, get ready for the new seasons. You have been warned. All right. We'll see you next time.